Algebra 2 Honors 6.5 notes. We're going to be using properties of logarithms to evaluate, to expand, and to condense. And so we have some properties of logarithms here. The product property, if we have log base b of m times n, we can break it up into their sums. So let's just look at an example. So say we have log base 8 of 4 times 5. We can break that up into log base 8 of 4 plus log base 8 of 5. And there you have an application. We're going to want to be able to go both directions. Start with the product and break it up into a sum, or take the sum and break it into, or go back into a product. With a quotient, we're going to want to be able to do the same thing. We have log base b of m divided by n, and so then we have the difference of their individual logarithms. And so say I have log base 5 of 3 divided by 2. I can break that into log base 5 of 3 minus log base 5 of 2. So the difference of their two logarithms. Again, we're going to be able to go both directions with that. Then we have the power product. Log base b of m to the n equals n log base b of m. And it's just that this power can come out in front. So if I have log base 3 of 7 to the 4th, I can write that as 4 log base 3 of 7. So those are the properties of logarithms. And so anyway, we're going to apply this in this next example. We see problems like this where we've given base 3 and the values of log base 3 of 4, log base 3 of 5, some approximations, and we're going to need to use those to evaluate. So you got to show detailed work to show how you use these. And we're going to apply these properties of logarithms. So in A, we have log base 3 of 4/5. Well, I can write that as log base 3 of 4 minus log base 3 of 5, and I have values for each of those. So I can replace those with their approximation. So log base 3 of 4 is about 0.8, oops, wrong one, sorry. Log base 3 of 4 is about 1.262, and log base 3 of 5 is the 1.465. And if you subtract those, you get a negative 0.203. And so there is the first value. In part B, we have log base 3 of 20. And it's like, wait a minute, 4 and 5, neither of those are 20. Well, you got to figure out how to write 20 in terms of 4 and 5. And in this one, it is simply the product of 4 and 5 is 20. So I can rewrite this log base 3 of 4 times 5. And then I can use the product property that says this is equivalent to the sum of their individual logarithms. Then I can replace those with their approximations that were given to me, and this is the work you need to show, and that adds up to be 2.727. Oops, 7.727. There we go. And then in part C, log base 3 of 25, we have 4 and we have 5, and oh, wait a minute, 25 is 5 squared, so I can write this as log base 3 of 5 squared. And then I can apply the power product that says if I bring that exponent out in front, I have 2 times log base 3 of 5. And then I can substitute 1.465 for log base 3 of 5, and then that comes out to 2.930. And you should have the 0 in that. Oops. There we go. So we have a few examples where you should try. So stop the video, try it, and then come back and see how you did. So how did you do? We have this log base 6 of 5 divided by 8, and we have both the log base 6 of 5 approximation as well as log base 6 of 8. So I can make this log base 6 of 5 minus log base 6 of 8. And then I can put in their substitutions. They're values that we have. They're approximations. And with that, I get approximately negative 0.263 for the evaluation of log base 6 of 5/8. You have to show detailed work so I know that you are using the approximation given. Then example 2, well, 40 is 5 times 8, so I can replace this with log base 6 of 5 times 8 and apply the product property of logarithms. This is log base 6 of 5 plus log base 6 of 8. And then make those substitutions. And those come out to be 2.059. And number 3, you should recognize that 64 is 8 squared. So I can write this as log base 6 of 8 squared. And the power property of logarithms is I can bring that power out in front, and these are equivalent. And then I can make the substitution. Approximately log base 6 of 8 is 1.161, and that comes out to 2.322. And number 4, well, 125 is 5 cubed. So I can make this log base 6 of 5 cubed. And then I can bring the 3 out in front using that power property of logarithms. And then I can make the substitution. Log base 6 of 5 is 0.898. And times 3, that is approximately 2.694. All right, so then moving on, another technique that we use especially in calculus with evaluating and being able to put something in a form that is more easily evaluated is expanding or condensing logarithms. And so in example 2, you need to expand this natural log. That means it's base e of 3x to the 5th over y. And so we have a product and a quotient, and that becomes natural log of 3 plus natural log of x to the 5th minus natural log of y. Product, you have the sum, and the quotient, you have the difference. But then when you expand, we don't leave this to the 5th power. We want just arguments that are not raised to a power. So we're going to use the power product and keep going. So where you need to go to is writing this as 5 natural log of x. So we have natural log of 3 plus 5 natural log of x minus natural log of y. And that is expanded. Well, you also need to be able to condense. So we have this next one where we have the common log of base 10. And before we start condensing, we don't want a coefficient other than 1. So we're going to do that reverse power rule of logarithms and rewrite this log base 6 plus log of 3 to the 4th minus log of 3. And then similarly to what we did, well, I guess it's in backwards of what we did with 2, we can rewrite this as log, and the sum we can put as a product in the numerator, and the difference, the argument, we're going to put in the denominator and divide by it. But then you need to simplify. And so I would say this 3 takes out one of those and makes that 3 cubed. So you have log of 6 times 3 cubed, which is log of 6 times 27, which is log of 162. And on that one, there are some different routes to take to get to the same answer. So anyways, we have some more examples. So how about stop the video, you try them, and see how you did. All right, so how did you do? Example 5. I can expand this by making it log base 6 of 3 plus log base 6 of x to the 4th. But we don't want to leave that x to the fourth. We don't want to leave that argument with something that has a power. So we're going to bring that out to the front and write it log base 6 of 3 plus 4 log base 6 of x. And that's how it should be written. In number 6, you got to be a little bit careful. You have a quotient. You have natural log of 5 minus natural log of 12x. But that 12x is really a product. And so now be careful on what you do with this. It's natural log of 5 minus, and it's the quantity. We're going to separate that natural log of 12x into the natural log of 12 plus the natural log of x. But then we have to distribute the negative, and our final answer is natural log of 5 minus natural log of 12 minus natural log of x. It is very common to miss the sign on the minus natural log of x and not have that as a difference. Then in number 7, condense the logarithmic expression. This is log base 10. It's a difference, so we're going to write that as a single logarithm of the quotient of x and 9. That's it. In number 8, I don't want this coefficient of 3 out in front. So I'm going to do that reverse property where I make that plus natural log of 3 cubed. And then I have this natural log of 12 that I'm subtracting. And then that becomes natural log of 4 times 3 to the third all over 12. But we can simplify that. We can say 4 goes into 12 3 times, so this natural log of 3 cubed over 3. And then this 3 can take one of those out, and I get natural log of 3 squared, and it leaves me with natural log of 9. So one more thing that we have in this section is changing base. And we use this change of base to simplify expressions, to be able to do proofs where we need things in the same base. Earlier on, when we didn't have calculators, there would be tables with logarithms evaluated for specific different bases. And so we'd have to change things to specific bases where we had values we could substitute. So anyways, there's a lot of different uses for this. It's something that you need as you move on. And so we have this change of base formula. Some of you will need it just to use your calculator to evaluate when the bases are something other than base 10 or base E. So let's say that we have base, say, 8 of 3. So we have this log base 8 of 3. I can change this to any base. And so I'm going to make this log base b over log base b. So that's what happens here. We have log base b, and then the argument of the original goes in the numerator, and the base becomes the argument of the denominator. So the 3 becomes the argument of the numerator, and the base of 8 becomes the argument of the denominator. So I can change this to any base I want. And 2 of them that you most likely have available on a scientific calculator are either log base 10. So if I make this log of 3 over log of 8, I can go ahead and evaluate using the base 10 on your scientific calculator. But since I can change it to any base, I can also change it to base E, which is your natural log. So natural log of 3 over natural log of 8. And irregardless if you use log base 10 or log base E on your calculator, you're going to get the same value for those two. And that's your change of base formula. Again, you need this for proofs, trying to get things into the same base to be able to keep working things. And in the case of some calculators don't have a change of base available for you, you have to be able to change them to log base 10 or log natural log, which has a base of e, to even get their value. And so examples of this is in example 4. It says evaluate log base 7 of 11 using common logarithms. You have to show change of base, and you will need a calculator. So log base 7 of 11, and you need to know common logarithms are base 10, and so we write it log over log. The base is understood to be 10, and the argument of the original goes as the argument of the numerator. The base of the original becomes the argument of the denominator. So now you can put this in your calculator, log base 10 of 11 divided by log base 10 of 7, and see what you get. And to 3 decimal places, this is approximately, it's supposed to be just approximately 1.232. Excuse me. All right. So that's using common logarithms. And so then using natural logarithms, we're going to evaluate log base 2 of 19. So I want this natural logarithm, so I'm going to use a natural logarithm in the numerator as well as in the denominator. That is a logarithm of base e, and that argument of the original goes in the numerator. The base of the original becomes the argument of the denominator. So now you can take your calculator, natural log of 19 divided by natural log of 2, and approximate this. 3 decimal places is 4.248.